You ever stop and think about what happens in that tiny little moment after you hit search? I mean, whether you're looking for a contact in your phone or some random product online, there's this hidden, brilliant world of engineering that makes it all feel, well, instant. Today, we're going to pull back the curtain and take a look inside. So how do they do it? Seriously, how can a system possibly sift through billions of records and pull out the one exact thing you need, like right now? It's a massive question, and it's one that has been at the very heart of computer science for decades. And the answer, well, the start of the answer anyway, isn't some kind of unknowable magic. It's actually a beautifully simple and incredibly powerful idea called the binary search tree. This is the foundation, the bedrock concept that makes all modern high-speed data searching possible.
Okay, so let's start with the promise. What is it about the binary search tree that makes it such a game changer for finding things fast?
You know, the genius is all in one simple rule. For any item in the tree, we call it a node. Everything to its left is smaller, and everything to its right is larger. Now just think about what that means for a second. With every single decision, you get to throw away half of the remaining data. It's like a game of 20 questions on steroids, and that's what makes it so unbelievably efficient. Let's actually watch one get built. Okay, we start with 5, that's our root. Now we insert a 2. Is 2 less than 5? Yep, so it goes to the left. Next up is 8. That's bigger than 5, so it goes to the right. See the pattern? 4 is less than 5, so we go left, but it's greater than 2, so it goes to the right of 2. Then 1 goes left of 2. Look at that. You get this nice, branching, balanced structure. This is a happy tree, a fast tree. But, and you knew there was a but, right? The binary search tree has this critical weakness, a real Achilles heel that can turn our super fast search into a slow, painful crawl. This is where our beautiful, simple solution starts to get a little more complicated.
So what happens when the data we're inserting isn't random? Imagine we feed it numbers that are already sorted. We start with 1, then we insert 2, it goes to the right, then 3 to the right of 2, then 4 goes to the right of 3. Oh no, look what happened. Our beautiful bushy tree has just collapsed into a long, spindly straight line. It's basically just a list now. And the performance difference here is just staggering. In our happy, balanced tree with 10,000 items, a search takes maybe 14 steps. That's what we call logarithmic time, or O log n. It means the search time barely goes up even if the data doubles. But in our sad, unbalanced tree, a search could take all 10,000 steps. We've completely lost our speed advantage.
So how do we fix this disaster? Well, the first really brilliant solution popped up way back in 1962. It's called an AVL tree. And you can think of it like a binary search tree that's a little paranoid. It's constantly watching itself, always vigilant, and ready to fix any tiny imbalance the second it happens. The secret sauce here is a strict rule called the balance factor. An AVL tree is always checking to make sure that for any node, the height of its left branch and its right branch never differ by more than 1. If an insertion breaks that rule, the tree immediately snaps into action. Let's see this little magic trick. We insert 10, then 20, then 30, and we get that problematic straight line. Uh-oh, the tree detects the imbalance. It then performs what's called a single rotation. The middle node, 20, just pivots up to become the new root. And boom, just like that, balance is restored. It's a proactive, self-healing system. Pretty cool, right?
But what if you don't need to fix things constantly in real time? What if you could just fix the whole tree at once, every now and then? This brings us to a totally different philosophy, the Day-Stout-Warren algorithm, or DSW. This isn't about constant vigilance. It's more of a nuke and rebuild approach. Now, I know what you're thinking. This sounds completely backwards, right? To balance a tree, the first thing you do is make it completely unbalanced on purpose. You literally transform the whole thing into that worst-case scenario, that long straight line structure we call a vine. The process itself is just fascinating to watch. You start with your messy, unbalanced tree, then you systematically use rotations to flatten it into that single vine. And then, once you have that, you use a very specific, calculated series of new rotations to build it back up into a perfectly balanced tree.
It's this radical tear down and rebuild that results in perfection.
So now we have two very different solutions on the table. The AVL tree is your go-to for dynamic databases where data is flying in and out all the time because it fixes problems as they happen. The DSW algorithm, on the other hand, is way more efficient if you're just going to load a huge amount of data once and then search it over and over. It's all about picking the right tool for the job.
But our quest isn't over, not by a long shot. See, all these solutions we've talked about work great as long as the tree can fit into your computer's super-fast main memory. But what about modern databases? We're talking terabytes of data that live on a much, much slower physical disk. And that introduces a whole new kind of bottleneck. This number right here, this is why it's such a massive problem. Getting data from a spinning hard disk is incredibly, painfully slow compared to getting it from memory. In the time it takes your computer to do one single disk read, it could have executed 200,000 other instructions. So suddenly, the name of the game isn't just minimizing comparisons anymore. It's minimizing how many times you have to touch that slow disk.
And the solution to that problem is the B tree. A B tree basically looks at the binary rule and says, "No, I'm good." Instead of having just 2 children, a single node in a B tree can have hundreds, maybe even thousands of children. This creates a tree that is incredibly short and wide. A B tree holding billions of items might only be 3 or 4 levels deep, which means you can find any piece of data with just 3 or 4 disk reads. That's a huge win.
And this finally brings us to the B+ tree, which is an evolution of the B tree, and it's what's running inside most of the databases and file systems you use every day. It makes a couple of key tweaks. First, it only stores the actual data in the very bottom layer, the leaf nodes. And second, and this is the killer feature, it links all those leaf nodes together in a sort of list. This makes it super efficient to scan through a whole range of data, like if you wanted to find all the emails from last Tuesday. So wow! We've been on quite a journey here, haven't we? We started with a really simple, elegant idea for finding things fast. We saw its critical flaw, and then we explored this whole family tree of increasingly clever solutions, each one designed to solve a very specific problem. You know, the big takeaway here is that every single one of these data structures is really just a bundle of engineering trade-offs. That simple binary search tree is a great start, but it's fragile. AVL trees give you that constant balance, but they're more complex to manage. DSW gives you absolute perfection, but not in real time. And B trees are just brutalist, efficient machines for reducing disk access.
And that's really the core lesson in all of this. In computer science, and really in all of engineering, there's almost never one single best answer for everything. The real quest for the perfect tree isn't about finding one ultimate solution. It's about deeply understanding the problem you're trying to solve so you can choose the tree and the trade-offs that are right for that specific job.
So the next time you search for a file on your computer or look something up in a database and you get that answer back instantly, just for a second, appreciate the invisible elegance behind it. Think about that complex little dance of nodes rotating, trees rebalancing, and data being pulled from a disk. All of it happening in a handful of milliseconds that you don't even notice. All just to bring you what you needed right when you needed it.